All right. Let me see if anyone's there. All right, I'll be back.
Genau написала, распределилось заявление на конференции.
All right. Okay. So let me get started on the lab. So, okay. So the first several problems are basically about uh about kind of manipulating strings, stuff like that, and showing what happens. So if you do something like this, so S is old string, and then you say S is new string. So to emphasize the point, I'll say S1 equals S, like this. So in order to show this, I need to render all objects on the heap. So that looks like this, right? So initially S points to old string and also S1 points to the same object. So technically S and S1 are aliases, but that doesn't matter because you kind of change the contents of the string. But the only thing you can do is you can say S is a new string. So that makes it so that S points to this here now. Okay. So it's not that S1 is affected, S1 is still the old string. Okay, so that's like this. So with lists, though, there are two things that you can do. You could say, for example, a list is something new, for example, geoval, and you can have a function that changes the contents of val, right? So how would that work? So if I have a function g, and here I say like L at 0 is 42. And then I have a function L, which returns something like, but maybe it returns the same thing every time, like 2, 3, 4. And then I can have L is equal to f of L. And I can have g of L. And let's see how that affects aliases. So let's say that I have initially L is 5, 6, 7. And then I say L1 is equal to L. So now L and L1 are aliases. Say L is equal to f of L. Say L1 equals L again, and then we'll see how that affects things. So let's run this. So initially L is 5, 6, 7. And then L1 and L are the same thing, right? So L1 is this list, which is 5, 6, 7. And L is this list, which is also 5, 6, 7. Now I'm saying L is equal to f of L. So that means that we're creating this new list, 2, 3, 4, and we're going to assign it to L. So if we are doing that, L1 doesn't care, even though L1 and L are currently aliases, because what I'm going to do is I'm going to create this new list, 2, 3, 4, and I'm going to make L be 2, 3, 4. Let's see what happens. So the return value is now 2, 3, 4, and now we're going to make L, instead of being 5, 6, 7, we'll make it this list, 2, 3, 4. Okay, so here again, I'm going to make L and L1 aliases. So L1 is currently 5, 6, 7. L is 2, 3, 4. I'm going to make them the same, 2, 3, 4. And now we're saying G of L. So when we're saying G of L, what happens is G, this L and this L are aliases. And inside of G, we're going to change the first element to a 42. Not returning anything. So, of course, L1 is also changed because L and L1 were aliases and remain aliases. Okay, so that's like that. So what happened? So in part B, what we're doing is first working just with aliases. So we can also work with copies. So what happens if instead of saying L1 equals L, L1 equals L here, we're saying L1 equals to L copy here, and L1 equals to L1 copy. So this is just another way of saying L everything. Just 1 second. All right. So what's going to happen if we do things like this? I'll stop rendering all objects on heap. So what's going on now is we have one list, 5, 6, 7, and now we have another list that's 5, 6, 7, like this. And now when we say L is equal to f of L, what's going to happen? Well, the new list 2, 3, 4 is going to be created. And instead of pointing to this 5, 6, 7, L is going to be pointing to 2, 3, 4. Right? So we're returning. Now L is pointing to 2, 3, 4. So it used to be 5, 6, 7, and now L is 2, 3, 4. And now we're doing the same thing again. We're saying L1 is a copy of L. So L is currently 234. So L1 is also going to be 234, like this. And then if we do G of L, well, that's going to change the value of 2 to 42, but it's not going to change L1. So that's like this. All right. So what if we do the same thing, but with a dictionary? Well, that's going to be different. So, or rather with a shallow copy of the dictionary, that depends what's going to be whether it's going to have lists as values. So initially, it's not going to have lists as values. So like we're going to do like exactly the same thing, except we're going to say like this is the dictionary. So it's like a dictionary with integers as keys. Doesn't have to be this way, but it could be this way. So that's exactly the same thing. Make this. So it's all exactly the same, right? So L is now a dictionary. We create a copy of the dictionary. We now change F to be something else. So L to be something else, sorry. Now L is something else. L1 is still the same. Now make L and L1 be the same. And now go and change the first element of L. So this guy to 42. Now it's 42. That's fine. So that's all fine. So it is going to be different if some of the elements here are lists. So let's say that I do something like this. So that's all fine. And in fact, for now, nothing's going to change. What is going to change is if I say L at 0 is 42 over here. Okay, so let's see what's going on here. So L right now is this dictionary that has lists as elements. Now we're going to make a shallow copy. So L1 is going to be this. But notice that this list, 5, for example, right, so this list kind of 5 and 6 and 7, those are all lists. And L1 at 0 is an alias, or rather L1 at 0 is an alias of L at 0. So that means that if you change L at 0, it's the same as changing L1 at 0. It's changing this guy. This is actually at 1. Okay. So, okay. So let me just look at it render the 5 for some reason. That's okay. Oh, that's because I. Right. So everything that I said before is correct, but now you're going to see the 5. So that's like this. So now when we say L is equal to F of L, the same thing happens. We're creating a new dictionary and we're making L be that new dictionary. So now L1 stays the same, but L is going to refer to a new dictionary to return value that just was built here. So now is the interesting part. So we're making L1 again be a copy of L. So now again, the elements are aliases. So L at 0 is the same as L1 at 0, where 0 is now a key rather than an index, but same thing. And now if we go to G of L and we change L at 0, what we're changing is this guy. So of course, that's going to affect it whether we access it through L at 0 or L1 at 0. So that's like this. So this 42 is now L at 0 and also 1 at 0. So note that if I didn't go L at 0, but rather went L at 0 is equal to something new, or if I wanted to make it symmetric and make it the list, I don't have to. Then this is what that's going to look like. So if I make L and L1 be a copy, then of course, again, I replace L with a new dictionary, L is a new dictionary. But now if L1 is a copy of L, despite this fact, if I say I want L at 0, so this guy to be something else, to not be this list that contains 2, I can. And that's not going to affect what this guy is, because it's not changing this guy. It's creating a new list and saying L at 0 is now going to be this new list. So that's what you're going to see is L at 0 is now this new list 42. L1 didn't change. It's still this. All right. So that's this question. So you can compute a deep copy of the dictionary using copy.deep copy. So deep copy just means, copy everything as deeply as you need. So let's do that. And in this case, well, like you're always creating independent copies, right? So over here, L and L1 are completely separate. They happen to be equal in this instance at first, but you change L to something else. Of course, L doesn't care, didn't care before either. Here, again, we're making L be equal to L1. So L is 2, 3, 4 here with, at 0, it's 2, at 1 is 3, at 2 is 4. And then it's the same over here. But if you change L at 0 to something, that wouldn't matter. Of course, that wouldn't matter before either. But I can also make it L at 0, and it still wouldn't matter. So the relevant part is the relevant part is over here, where we have L and we have L1. They are currently equal in terms of all the numbers, but they're also different objects. So if we go to L at 0, that's this guy, that's going to change to 42, but that doesn't affect this guy because we made it so that L1 and L are two copies of the same thing, but they are completely separate from each other. Except technically the integers are aliases, but that doesn't matter because you kind of change the contents of the integer. So here I made it 42. I could have also made it like the number 42, and in which case it wouldn't be like the list 42, it would be the number 42. Let me do that just so that you see it. So that is like this. All right. Okay, so we are doing this code. do this, left, that's like this. And we'll just check that it works. Okay, so 6 is at location 1, that seems fine. 12 is at location 4, that seems fine. 20 is nowhere, so that's none, so that is O. So let's say that we want to return the number of iterations, right? So how do we do that? Well, basically, every time we run this, we increase the number of iterations. This, and we'll return the number of iterations as well as the answer. So we just, again, increment number of iterations every time by 1. And at the end, every time we return something, we also return the number of iterations. So, okay. For example, this took 2 iterations. Right. We should note that really this should be 1, because when we're returning here, we are like this. So when we are returning over here, we are returning 1 fewer iteration than we need. So what I'll do is I'll just increment by 1 at the top instead of at the bottom. So that would be this. So this is 2 iterations. And then this is 1 iteration. 1 iteration seems like it's not really enough. Let me see. And what we got lucky. Oh, it's in the middle. Okay, 123 is going to be more. Yeah, so 123 took 2 iterations. So here we take care of the situation where high minus low is at most 1. So if I add a few numbers here, well, it's now taking 2, 7, 8, 9, and take 2. So in order to get more, you need kind of a lot more numbers. So this. So now that takes 3. Okay. So, all right. So we've done that. So in the worst case, binary search returns early. Okay. So what would be a way to construct the list L such that that never happens? Well, trick question. Like it never happens when L mid is not equal to E. That's it. So now we have like lists of sizes 10 and 100 and 1000 and so on. We want to output the number of iterations that the while loop takes in the worst case. So how do we do that? Well, we just give it sorted lists where the element is not there. So we'll construct those. It's nothing. And then initially the length is 10. So I can construct a thing that's like this, that's technically sorted. If I define like first of all. And then I can look for 1 or something in that list. So let's do that. So let's do it 20 times. So here I get the answer and I get the number of iterations. A binary search. And I'll say length times 0 just to make a big list. And I'll say that I'm looking for a 1. And I'll append editors to the list of editors. Okay. So now I can look at any cell. Oops, I forgot to increase length. So now length is going to be 10 and 100 and 1,000 and so on. So now that's going to take a little bit more. In fact, a lot more. Let's not make a list that's this long. So that's still like 10 to the 10. That's not like a little bit. So that's fine though. So now we can look at any choice out. And that is what it looks like. So every time it increases by about 3, which makes sense because the number of iterations is log 2 and log 2 10 is like 3 point something. 0.1, I think. Great. So that means that every time that you increase the thing by 10, you add approximately 3.3, right? So log 2 times 10 is equal to log 2 100 plus log 2 10. That's just how logs work. So that means log 2 100 plus 3.3. So you're adding 3 every time. The number of iterations is approximately log 2n. So here what we see is we're adding approximately 3, in this case exactly 3 every time to the number of iterations. So what was the largest list that we made? Well, we multiplied 10 by itself 7 times. We started with 10, so 10 to the 8 is a list of length 100 million. So, okay. So here we indeed stopped at 100 million as well. So we can do the same thing, but using time.time. So what we want to know is how long it's going to take to run every iteration. Sorry, how long it's going to take to run every one of the calls in terms of seconds. So how can we do it? So here, instead of counting iterations, which we can still do, we can say, how much time did it take? So you can do it externally. We did that in lecture. Let me return the time in here. Actually, let me not do that. So I'll write the function time it again. So it's going to be time it function, and it's going to be the input. One and two, I guess. And start time is going to be time. And I'm going to do it 100 times. 500. So this is the same as lecture, so I'm not going to spend a lot of time on it. with this. And here I'm going to have times, and initially it's going to be empty, and I'm also going to append this. So I'm basically calling the function timeout here. Nothing for time. Now I have it, and now I have times. So the times look like this. Here we have, and it turns out they look like this. Let's plot those one against each other to see that they correspond. So I'm going to plot times lengths on the on the x-axis, and the times the y-axis. And it's approximately what you would expect. The differences aren't huge, so there's kind of like some variation that's just due to kind of random fluctuations. We could increase this number by a bit and probably get a nicer curve. So that's kind of approximately linear. If we just increase the number of times that we repeat the thing more, we get a nice linear curve. Well, because the number of iterations does correspond to the runtime linearly. I think that's it. Thank you.